let's look at the concept of a Cauchy sequence. So we start by giving the definition. A sequence of real numbers is called Cauchy if, for every epsilon greater than 0, there's an index after which the distance between any two terms is less than epsilon. So just to compare and contrast Cauchy versus convergent, in a convergent sequence, the terms get arbitrarily close to the limit, right? And the key thing you're looking at is the distance between the term, the nth term, and the limit. And you can make that as small as you want if you go far enough out into your sequence. On the other hand, a sequence is Cauchy if the terms get arbitrarily close to each other. So the distance between terms, not necessarily consecutive terms, but just the distance between any terms can be made arbitrarily close if you go far enough out into your sequence. So let's get started here. The way to understand some of these concepts and the definition of Cauchy is to actually look at some properties of Cauchy sequences. So the first thing we'll prove is that if you have a sequence that's convergent, it must be Cauchy. Okay, so let's see here. Now, how are we going to get this? Remember, we said convergent means that your Sn minus S, the distance between Sn and S is arbitrarily small. Cauchy means that the distance between terms is arbitrarily small. Okay? This is what we want. And this is what we know already. So let's see here. So if you fix epsilon greater than 0, then, let's do this. Notice that the distance between Sn and Sm is the same as the distance between Sn minus S plus S minus Sm. Or not the distance, but so this absolute value is the same as this absolute value, right? And now we can use the triangle inequality to say that the distance between Sn and Sm is less than or equal to the distance between Sn and the limit and the distance between Sm and the limit. So again, kind of think of it like, people trying to leave a door, right? And you have a whole bunch of people, and the people are arbitrarily close to the door. If a sequence is convergent, that means that the people are arbitrarily close to the door, okay? If a sequence is Cauchy, that means the people are arbitrarily close to each other. So the essence of our proof here is to say, well, yeah, the people are arbitrarily close to each other because if you take two people, they're close to the door. We can make them close to the door. And so their distance, the distance between the two people, has to be less than or equal to the sum of the distance between each person and the door. So that's kind of what we're doing. Now let's go ahead and make this, we can do a formal proof here right quick. So let's do a proof. So we'll say hypothesis, Sn is convergent. Claim, Sn is Cauchy. And then for the proof, we'll say since Sn is convergent, there exists some real number S, which is its limit, right? Let S equal the limit of Sn. This is guaranteed to exist by hypothesis. Yeah, since Sn converges. Okay, now we'll say fix epsilon greater than 0. There exists an n Since Sn converges to S as n goes to infinity, there exists an index n such that little n bigger than n implies the distance between Sn and S is less than epsilon over 2. Okay. Now for any n and m bigger than n, the distance between Sn and S is less than epsilon over 2, and the distance between Sm and S is less than epsilon over 2. So the distance between Sn and Sm will be less than or equal to epsilon by the triangle inequality. Okay. So just to recap, the moral of the story is that convergent implies Cauchy. Now let's look at another property. We're going to say Cauchy sequences are bounded. So Cauchy implies bounded. And the proof for this is going to be similar to the proof that we did, which showed that convergent sequences are bounded. And again, you have this idea, or this time I'll draw a number line. So we know that we can make the terms arbitrarily close to each other, right? And then there'll just be a few terms, finitely many terms, that are not within epsilon of each other. So the idea is that overall, the terms have to be bounded. So let's see here. So we fix epsilon greater than 0. Then there exists an n such that little n bigger than n implies the distance, or n and m, the distance between Sn and Sm is less than epsilon. So now think about our terms here. So we've got S1, S2, S3, Sn, Sn plus 1, Sn plus 2, da, 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 da. And we're saying that after this point, any of these terms here are within epsilon of each other. So in particular, any of these terms are within epsilon of this one. Okay, so what I'm going to do is I'm going to say, so m bigger than n implies the distance between Sn plus 1 and Sm is less than epsilon. So that means Sm is going to be less than Sn plus 1 plus epsilon and greater than Sn plus 1 minus epsilon. Yeah? So I have a bound on all of these terms, right? All of the terms where m is bigger than n. They have to be in between this and this bound here, okay? So I'm going to say let m1 equal the max of Sn plus 1 plus, oh, let's just let epsilon equal 1. Right, it's true for any epsilon, so in particular, is true for epsilon equals 1. So the max of that, this number right here, and S1, S2, dot, 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 all the way up to Sn. And then let M2 equal the min of Sn plus 1 minus 1, because I'm trying to set up a lower bound. So all of my S1s, all of my SMs are bigger than this number here, when n is bigger than or equal to big N. So all these terms are going to be greater than or equal to S sub n plus 1 minus 1. So a lower bound will be the minimum of this number and all of these numbers. Okay, and then we'll say then for all n and n, M2 is less than or equal to Sn, less than or equal to M1. Okay, so we have a lower bound and an upper bound, and that's equivalent to saying that my sequence is bounded. Okay. And this sketch is good. This is good practice, is to go back and write the proof based on the sketch that we've done here. Okay? And so the bottom line is that Cauchy sequences are bounded. And now let's get to the big theorem. So the big theorem says in R, right? So that's the realm in which we're working. In terms of real numbers, a sequence is convergent if and only if it is Cauchy. And I'm going to contrast that with in Q. It is not the case that convergent if and only if Cauchy. So you can have a sequence, and let me put here in Q. So Sn is a sequence of rational numbers. Sn converges in Q if and only if, here's my definition, there exists a rational number such that for every epsilon greater than 0, there exists an n such that n bigger than n implies the distance between Sn and S is less than epsilon. And so the key thing here is we're requiring the limit to be in Q, right? Here's the deal. You can have a sequence that is Cauchy in Q, but it does not converge in Q because Q has holes. i.e. is not complete, does not satisfy the completeness axiom. There exist sequences in Q that are Cauchy, but do not converge in Q. So this doesn't happen in R. Because R is complete. right? So any Cauchy sequence in R will also converge in R. And so can you think of an example? And so, I mean, we're going to prove this, right? I can't just say this. This is a big deal. We're going to prove that every Cauchy sequence in R converges in R. But can you think of a sequence in Q that is Cauchy, but it does not converge in Q? Well, here's an example. Take any sequence in Q, sequence of rational numbers that converges to an irrational number in R. So an example would be 3, 3.1, 3.14, or even E, right? So do you remember e to the x is expressed as a power series as x to the n over n factorial? So e to the 1 is just going to be 1 over n factorial, which means e is the limit, n goes to infinity, of the partial sums. Do you remember this from calculus? So the first one would be 1. The second one would be 1 plus 1, which is 2. The third one would be 1 plus 1 plus 1 half. The fourth term would be 1 plus 1 plus 1 half plus 1 over 3 factorial, and so forth and so on. Each of these numbers is rational, but their limit is an irrational number. So if I'm in the land of Q, I don't know about the existence of E, right? I know about these numbers, and these numbers will be Cauchy. Why will this sequence be Cauchy? Because this sequence also lives in R. And in R, this sequence converges to E. And in R, we just proved that convergent sequences are Cauchy. So this sequence is Cauchy. It's Cauchy in R, it's Cauchy in Q. It converges in R, however, it doesn't converge in Q because its limit would need to be an irrational number. And if you're living in the land of Q, you don't know that irrational numbers exist. So in Q, here's an example of a sequence of rational numbers that are getting close to each other, but in Q, they're not getting close to any limit. So they're just kind of bunching up around a hole where we know that's E, but if you're in Q and you don't even understand what a irrational number is, that doesn't make sense in the land of Q, then the terms are just bunching up, right? They're getting arbitrarily close to each other, but they're not getting arbitrarily close to another, like a limit in your space. Okay, so I just wanted to point that out, that when we say convergent if and only if Cauchy, that is only in R, and that is only because we have the completeness axiom. If you don't have the completeness axiom, your space might have holes, and in which case you can have sequences that are Cauchy but are not convergent. because the limit is missing, if you will. Okay? So let's go ahead and prove this. So it says a sequence is convergent if and only if it is a Cauchy sequence. And the first step is to recognize that we have an if and only if statement here, right? So we're trying to say convergent if and only if Cauchy. So that means we really need to prove two things. Convergent implies Cauchy, and then Cauchy implies convergent, okay? Well, we kind of already proved step one, right? Didn't we prove that convergent implies Cauchy? Yeah, that was our lemma here. Convergent implies Cauchy. So the only thing we need to prove is this one down here, which is that Cauchy implies convergent. In other words, every Cauchy sequence in R converges to a real number in R. And so I've kind of written this down here. Step one follows from the last lemma on slide 19. And then step two, here's how we're going to prove that Cauchy sequences are convergent in R. Well, now, Cauchy sequences are bounded. We just proved that. And bounded sequences that satisfy the lim sup is equal to the lim inf converge. That was the theorem we had on slide 16. So remember, we said that one way to determine if your sequence converges is by seeing if the lim sup and the lim inf agree. Because you can have a sequence and its limit doesn't exist, but its lim sup and lim inf will exist, right? By the completeness axiom, those will exist. They might be plus infinity or minus infinity, i.e. the sequence is unbounded. But if your lim sups are equal, lim sup and lim inf are equal to each other, then your sequence converges, assuming your sequence is bounded. And if they are not equal to each other, then your sequence diverges, right? Assuming your sequence is bounded. If your sequence is unbounded, then your lim sup is going to be like plus infinity, or your lim inf is going to be minus infinity, and you may or may not diverge to plus or minus infinity, okay? But the theorem on slide 16 says that if you have a sequence that's bounded, and you can prove that its lim sup is equal to its lim inf, then you can conclude that the sequence converges. Our goal is to prove that Cauchy sequences converge, right? So Cauchy implies converge. That's our goal. So we'll say first, Cauchy implies bounded, done. And if it's bounded and the lim sup is equal to the lim inf, then we're done. So we want to show that the lim sup is equal to the lim inf, okay? So now how do we do that? Well, one way to show that the lim sup is equal to the lim inf is to show, so how are we going to do this? Let's see here. So first, lim sup of Sn is always, and I think you don't really need the parentheses, so always lim sup of Sn is bigger than or equal to lim inf of Sn, because your sups are always bigger than or equal to your infs when you're talking about the same set. So we just need to show that lim sup is less than or equal to lim inf. Because if we can prove that lim sup is less than or equal to lim inf, and we already know that lim sup is greater than or equal to lim inf, that will allow us to conclude that lim sup is equal to lim inf. And once we know that, we'll say, oh, lim sup is equal to lim inf, and our sequence is bounded, therefore our sequence converges, okay? So this is what we want to show, and here's how we're going to do it. We're going to show that for every epsilon greater than 0, lim sup is less than or equal to lim inf plus epsilon. So we want to show for every epsilon greater than 0, lim sup of Sn is less than or equal to lim inf of Sn plus epsilon. Okay, so we need that epsilon. We're going to use this epsilon to play around with upper bounds and lower bounds and the existence of, right, of, you know, certain terms. So if we show for every epsilon, lim sup is less than or equal to lim inf, that's going to imply that overall lim sup has to be less than or equal to lim inf. Okay? So let's get started with this. Here's what we're going to do. We're going to say fixed epsilon greater than 0. Okay, so our goal, just to remind us, is that lim sup of Sn is less than or equal to lim inf of Sn plus epsilon. Now, remember, what is lim sup? You have your S1, S2, S3, da, da, da. You look at the supremum of this set, that's your first U1. Okay, now what's the supremum of this set? That's going to be U2. What's the supremum of this set? U3. So you're looking at the supremum of the tail end of your sequence. That forms a brand new sequence. And that sequence is decreasing, because if I remove an element, my sup can only stay the same or decrease, right? I'm not going to end up having a higher sup than I did when I was in a bigger set, right? So I have a sequence of decreasing terms. If I'm decreasing and I'm bounded, then I have to converge, right? Because monotonic plus bounded implies convergent. And that limit is your lim sup. So it's literally the limit of the sups of the tail end of the sequence. And then similarly for the lim inf. So once we have our epsilon, let's just start off by using the fact that we're going to assume Sn is Cauchy, right? So we'll say Sn Cauchy implies there exists an index n such that for all n and m bigger than n, the distance between Sn and Sm is less than epsilon. Okay? So I'm given the epsilon as fixed. Now I can go far enough in my sequence to guarantee that all of my terms are within epsilon units of each other. But another way of rewriting that is to say for all n and m bigger than n, let's see here, Sn is in between Sm plus epsilon and S sub m minus epsilon, right? So notice this means, ignore this part right here, but this means that Sm plus epsilon is an upper bound for the set of Sn where n is past big N. So I have an upper bound, right? So this implies that for each m bigger than n, Sm plus epsilon is an upper bound for the set of Sk such that k is bigger than n. Okay. Now, I have an upper bound for this set. That means Sm plus epsilon is less than or equal to is greater than or equal to the sup of the set, because the sup is the least upper bound. Yes? So for all m, Sm plus epsilon is greater than or equal to the sup of the set of Sk such that k is bigger than n. Okay? Well, now, that means this sup is a lower bound for the set of Sm plus epsilon, or m, right? And to make this easier to see, for all m bigger than n, Sm is bigger than or equal to that soup minus epsilon, yeah? So this is now a lower bound for the set of Sk such that k is bigger than n, right? Because this number is less than or equal to all of the terms past n. So it's a lower bound. The greatest lower bound is the nth. This is a lower bound, so it has to be less than or equal to the nth. The nth of the set of Sk, such that k is bigger than n, is bigger than or equal to this lower bound. Okay. So, remember, our nths form an increasing set. So say if your set of terms are in here, right? Your nths are the greatest lower bounds. Once you are looking at a smaller set, the nth is only increasing, right? So this nth, the nth here, has to be less than or equal to the lim nth. And similarly, the soup is bigger than or equal to your lim soup. Because remember, your soups form a decreasing sequence, right? Because you're looking at these nested sets. And so the soups will only stay the same or get smaller as you remove elements from the set. So the soup of this tail end of the sequence is bigger than or equal to your lim soup of your sequence. Therefore, this part right here, now remember, the nth is less than or equal to my lim nth, and my soup is bigger than or equal to my lim soup. So we'll have lim nth of Sn bigger than or equal to lim soup of Sn minus epsilon. And that's what we wanted to show, right? Remember, our goal was to say that if you give me any epsilon, I'll show you that lim soup is less than or equal to lim nth plus epsilon. I've done that here, right? So that means lim soup has to be less than or equal to lim nth. Okay, so let's say I think we'll go back over instead of me rewriting it, because I kind of wrote out everything. So our theorem is convergent if and only if Cauchy, and this is in R. Okay, convergent in R if and only if Cauchy. So convergent implies Cauchy. That's going to follow from a lemma that we did. Now, to prove that Cauchy implies convergent in R, we kind of coupled two facts. First, our sequence, if our sequence is Cauchy, then it's bounded. And then we wanted to prove that the lim soup is equal to the lim nth, because if the lim soup is equal to the lim nth and it's bounded, that means that it converges to a real number. So the reason why we need it to be bounded is so we don't get that SN diverges to plus infinity or something like that, right? So converges to a real number. So we wanted to show that lim sup is equal to lim nth. And we said, well, we always have that the lim sup is bigger than or equal to lim nth. So we just need to show that it's less than or equal to lim nth. And the way we need to do that is to show that lim sup is less than or equal to lim nth plus epsilon for any epsilon greater than 0. So we said fix epsilon greater than 0. Suppose your sequence is Cauchy. Then we can get it so that the terms are close to each other. And by manipulating the epsilons and looking at sups of different sets, we were able to conclude that the lim nth is actually greater than or equal to the lim sup minus epsilon. Okay? So, there we go. We now know that convergent in R, if and only if, Cauchy in R. Okay? So the things that we've proved, convergent in R, if and only if Cauchy, Cauchy implies convergent, Cauchy implies bounded, convergent in Q, or Cauchy in Q, it is not the case that Cauchy in Q implies convergent in Q. Yeah. All right. As usual, let me know if you have any questions.